Professor, can we start?
Yes.
Greetings, everyone who are present here over Zoom as well as on YouTube. This is the 5th lecture for quantum chemistry lecture series on quantum chemistry on quantum computers. The lecture title is Variational Quantum Algorithms. So, over to you, Professor Sugisaki.
Thank you very much. So, welcome to the lecture series of quantum chemistry on quantum computers. And today I'm going to talk about the variation quantum algorithms. But before starting this topic, I will give you answer of the exercise in the previous lecture. In the previous lecture, I gave you an exercise problem. So that we have a Chebyshev Hamiltonian on the form of Hamiltonian equal 0.5 times x0, x1 plus 0.5 y0, y1, and construct a quantum circuit on IBM Q for the time evolution operators with t equal pi. So here, it is substituting t by pi, and then simulate the time evolution with the following condition. The starting from the 1 state by adding an xk, power xk before the time evolution circuit, and measure the total QPE at the time evolution, and set the evolution time t equal pi over 4, pi over 2, 3 pi over 4, and pi, and run the circuit with these different time evolution lengths, and check the measurement outcome, and then run the quantum circuit using real IBM quantum machine, not simulator, and check the measurement outcome. And the result is something like this. This is the screenshot of the IBM Q quantum experience website. And this is the quantum circuit for the time evolution operators of the corresponding to this time evolution. As you can see, this is the first we have to apply a power x to generate the 1 state, and we have to applying the total decomposition. We can decompose the time evolution operator as a 2 exponential operators with only 1 power string in each exponential operator. So in this case, first we apply a exponential minus 0.5i y0, y and t. So this, the quantum circuit corresponding to this exponential operator can be written as, can be constructed as shown here. First we apply our x with pi over 2, and then apply single j, and then apply RCJ. And the rotation angle of the RCJ corresponding to t, the evolution time. And then for that, we have to apply another single j and our xj with the rotation angle equal minus pi over 2. And then apply quantum circuit corresponding to time evolution operator. So here, this can be realized by applying 2 Agamal gauge and single and RC and single and 2 Agamal gauge. And the results comes something like this. Actually, this Hamiltonian was derived by applying a Jordan-Wiener transformation to the Hamiltonian in the quantum form. So here, so this corresponds to the Rabi oscillation between the ground and a steady state in 1 electron system. I mean, the Q system has 2 states and 1 electron. But let's think about the hydrogen molecule, sorry, hydrogen atom, for example. Let's think about the 1s and 2s objects. Electron in the 1s object. And this corresponds to the 1 electron excitation, and this is corresponds to the d excitation. So under this Hamiltonian, the quantum state changing from starting from one state, the quantum state, evolution quantum state evolved to the one state and then return to the original state with a period of pi. So if we perform the quantum static estimation, the measure outcome should be something that plot in blue. Of course, we start the one state, sorry, one state, and this corresponds to some kind of flip-flop excitation. So the probability of obtaining the zero state and one state and one state are always zero. And then if, but starting from the one state, applying the time evolution operator, we can obtain the 0, 1 state at the time t equal pi over 2, and then return to the original state at the time evolution time t equal pi. But if we perform the same time evolution simulation on real quantum computer, the result is something like this. In the plot in red, and this is the result I obtained from the IBM manual. As you can see, there's small probability to obtain the 0 state and 1 state, and this is a result of some errors arising from the error or noises inherent in real quantum devices. But anyway, the time evolution on the real quantum computer approximately follows the result of the use obtained from the state vector simulator. So we start the topic of the variation quantum algorithm. As you can see, the real quantum devices currently available is very noisy, and the number of quantum qubits is about at most 50 or 100 qubits. So this the number of qubits is too small to implement quantum error correction. So we have to perform some computation under the noises or errors. Also, the number of executable coherent gates is at most 1,000 or less. So basically, in the previous talk, I explained how to construct the quantum circuit for the time evolution operator, which is required in quantum phase estimation based full CI. But the quantum circuit for quantum phase estimation based full CI is too deep to execute on these devices. So basically, the QPE is very promising for quantum chemical calculations, but currently it's almost impossible to execute on these devices to obtain meaningful results, especially for larger molecules. So under such circumstances, the variation quantum eigensolver was proposed in 2014, and variation quantum eigensolver, or VQE, is a quantum classical hybrid approach that is executable on these devices. Of course, the quantum phase estimation also uses classical computers for post-processing, pre-processing, but in VQE, we use the classical computer as well as quantum computer to compute every time. I mean, in the VQE, we perform some quantum circuits to generate the wave function, correlated wave function, and then calculate the energy expectation values, and then the information of the energy or measurement outcome is transferred to the classical computer. And classical computer perform the variation optimization of the parameter. The parameter appear in the appearing here. I mean the in VQE, quantum computer perform the execute the parameterized quantum circuit to generate the correlated wave function. So the quantum circuit includes some parameters. Classical computer performs the variation optimization of parameters, and then updated parameters are transferred to the quantum computers, and then perform another wave function preparation and energy expression value evaluation on quantum computers with updated variation parameters. So this optimization cycle are iterated until convergence. And this is the basic idea of the variation quantum eigensolver. And the first application of VQE using their quantum computer was using the photonic quantum computers. And the results were reported in this paper in Nature Communications. And they calculate the potential energy curve of the electron ground state of helium hydride. Helium hydride cation molecule. And they use the unitary ansatz to calculate to compute the correlated wave function, and they use QPE for wave function trace. So what is the unitary ansatz? So if you have experience of performing quantum chemical calculation on classical computer, you probably heard about the couple-cluster method. Couple-cluster method is based on the nonlinear expansion by using exponential. So here, let's think about the CCSD, single and doubles. In this case, this T1 and T2 are 1 and 2 electron excitation operators acting on the Hartree-Fock difference state. In the unitary couple-cluster method, we apply exponential tau instead of exponential t. Well, tau is written consists of t minus t dagger. So because the t is excitation operator, so t dagger corresponds to the d excitation from the virtual to occupied orbitals. And this unitary couple-cluster method, in the unitary couple-cluster method, the energy can be calculated by using this equation, just using the equation for the expectation values. And we can obtain this equation. And this term, exponential minus tau, h exponential tau, can be rewritten by using Baker-Campbell-Hausdorff expansion, as shown here. But unfortunately, this BCH expansion doesn't terminate for unitary couple-cluster because tau contains the excitation operators as well as excitation operators. So in order to solve this unitary couple-cluster on classical computers, we have to truncate the expansion of certain order. However, this exponential tau is a unitary operator, and quantum computer is capable of performing unitary operation. So basically, applying this unitary couple-cluster method on quantum computer is quite straightforward. And the contraction of the quantum circuit for corresponding to the exponential tau is very straightforward as discussed below. Another important point is, so if we can generate the quantum charges corresponding to exponential tau, we can calculate the expectation value of the energy by using this equation. So because we have an expectation value of the energy, we can apply this variation principle to optimize the unitary coupled wave function. So the unit energy can be calculated variationally. This is a very important point. And when I think about the UCSD case, the tau can be rewritten as a t minus t lower, and t is the excitation operators, and the data is the excitation operators. So we have to construct the quantum circuit corresponding to these cluster operators. So in order to perform this computation, first we have to apply a Fermi cubic transformation to obtain the corresponding Pauli operators. In the case of Jordan-Wegener transformation, these one electron excitation operators are transformed to two Pauli strings with XZZY and YZZX. Applying so the excitation exponential operator, cluster operator can be rewritten as shown here. So we have exponential function with two Pauli strings. But if we apply a total decomposition, we can obtain these two exponential operators with only one Pauli string in each operator. So the next step is to construct the quantum charges corresponding to these exponential operators. The construction of this excitation operator is very straightforward and very similar to the time evolution operator, as I talked in the previous talk. Let's think about the excitation operator, exponential ITIA over 2 times X3, Z2, Z1, Y0 terms. In this case, first we have to perform RX on the QB acting on the Y Pauli Y operator. And also we have to apply an Agamal gate to the QB acting on the Pauli X operator. And then perform signal ladder. And then perform the RC gate. Importantly, in the previous, in the time evolution operators case, the rotation angle was 2GT or something. But in the intercoupled cluster answers, the rotation angle should be minus TIA. This value can be derived by think about this RC, the matrix form on the RCJ. After that, we have to apply another signal ladder in the reverse order, and then apply another RXJ with the rotation angle minus pi over 2 to the QB. So Pauli Y operators. And also we have to apply another Agamal gate. The situation is all the same for this excitation operators. So basically, we can generate the Unitary crystal wave function on quantum computers by using the quantum circuit shown here. So, but in order to obtain the energy, perform the ESCC calculation, we have to calculate the energy expectation values. So let us think about the Hamiltonian given here. This is a Hamiltonian for hydrogen molecule with QPE based and applying the Bragg-Style transformation and apply 2-qubit regression by using symmetry. Energy expectation value can be calculated, shown here. So we have to evaluate the expectation values of the Pauli operators, for example, Z0 or Z0, Z1 or S0, S1 or Y0, Y1, and so on. So the equation value can be calculated statistical manner by applying the wave function preparation and following measuring several times, many times. So because the quantum computation is performed on the Pauli C basis, the evaluation of the equation value of the operators contain only Pauli C terms. It's very easy. Let us think about the situation. We perform the measuring, state preparation and measuring by 1,000 times. And measure outcome was something like this. Because the Pauli C operator is defined as shown here, so the eigenvalue of the Pauli C is 1 for the 0 state and -1 for the 1 state. So the expression value of the Pauli C 0 term can be calculated as shown here. This 1 corresponds to the eigenvalue of the 0 state, and 15 plus 124 comes from the frequency of the measuring outcome of the 0 state and 1 state. So as the measuring outcome of the first qubit is 0. And -1 times this -1 corresponds to the eigenvalue of the 1 state, and times the probability of obtaining the 1 state, which can be calculated 823 plus 38 divided by 1,000. So we can obtain the expectation value of the C1 state by applying this equation. For the C0, C1 state, the operator of C can be expanded as shown here. This is the this 4x4 matrix was obtained by a direct product of Pauli C times Pauli C. So as you can see, the eigenvalue of the Pauli CCJ, Pauli CC operator, is 1 for the 0 state and 1 state. And the eigenvalues is -1 for the 0 state and 1 state. So we can calculate the expectation value of the CC operator by using this equation. This is the probability to obtain the 0 state, and this corresponds to the 1 state, and this is the 1 state, and this is the 1 state. But of course, the Hamiltonian includes not only the Hamiltonian term contained on only power 3 operator, but also some operator, including power x or power y. In order to calculate the power expression value of the x0, xy terms, because the measuring of quantum state are carried out in the power 3 basis, so we have to perform the basis rotation from x to 3 by applying Eigenvalue. So this Eigenvalue can change the basis from x to 3. So by applying this Eigenvalue, we can obtain perform this quantum calculus several many times. We can calculate the expression value of the power x0, x1 terms. Similarly, in the y0, y1 terms, we have to apply the Rx gauge with the rotation angle pi over 2 to perform the basis change from y to z basis. So this is a general case. In case of evaluating x0, z1, x2, y4, z5, y6 term, the quantum calculus for evaluation can be written as shown here. Applying Eigenvalue to the QPE, we want to evaluate the power x operators, and we have to apply Rx gauge to the QPE of corresponding to the y operators, and then measure the quantum state. In this case, the measurement of QC is not necessary because there's no pi operator acting on QB3. But in principle, the expression value can be calculated by using the statistical manner. But expression value of mutually commutative power string can be evaluated simultaneously. So it means expression value of power string those are not commutative cannot be evaluated at the same time. So let us think of the power string containing only power 3 terms, something like this. We can easily confirm that these operators are commutative to each other. So we can evaluate all the terms at the same time. Also, power string having no identical QPE indices, for example, x0, x1, and y2, y3, can be evaluated simultaneously. So in this context, Hamiltonian term grouping is very important to reduce the measuring cost in VQE. So we have a QPE Hamiltonian consists of the linear combination of power strings, and we have to perform grouping as shown here. So as to the pi operators within the group are all commutative to each other. In order to make grouping, we can calculate the expression value of all operators, for example, in group 1 simultaneously. So the Hamiltonian term is about the order of n to the 4th power, but the measuring cost becomes about the order n to the 3rd power by applying this grouping. And also, we have to perform the variation optimization of parameters. This parameter optimization was usually performed by using gradient free or gradient using gradient approach. And the selection of the optimization algorithm is very important. This is the result of VQE simulation of the regional hydrogen molecule with the regional H bond distance equal 3.0 angstrom. So the regional H bond is almost dissociated. Perform the VQE with UCSP answers in conjunction with SQCG based set. The result of the optimization was something like this. In this paper, I examined 3 different optimization algorithms, Negami and Power and Cobler. As you can see, if we use the Negami algorithm, the variation optimization sometimes trapped to the static state or a local minima. So in this case, the selection of initial parameter is very important. And if we use power or Cobler cases, we can obtain the ground state regardless of the initial parameters. But in VQE, we can calculate the analytical gradient of the parameter if the parameter appears in the single Pauli strings. Let us think about the answer consisting of this kind of exponential Pauli operators. So the energy can be calculated as shown here. And for convenience, we write this term as psi, and this term as A, and this term as psi. So E can be rewritten as psi, this exponential operator, A, exponential operator, psi. So we want to calculate the gradient of the theta k. So we want to calculate delta E, delta theta k. So this calculation can be done by using this expression. So let us rewrite this term as B. So this corresponds to this gradient can be calculated as a commutator Pk and B. B is this operator. Importantly, this commutator can be calculated by using this equation. We can rewrite this B parameter by using this original A parameters, A operators. The result can be shown here. So substituting this equation into this equation, we can obtain the gradient by using these terms. So as you can see, these terms can be calculated by using the quantum circuit by substituting theta k by theta k plus pi over 2. And this term can be calculated by using the quantum circuit by substituting theta k by theta k minus pi over 2. So basically, we can calculate the analytical gradient by using 2 separate VQE simulations with the rotation angle theta k plus pi over 2 and the rotation angle with theta k minus pi over 2. So far, we discussed the unitary calculation answers, but there are many other answers proposed one. So, and this is the one of the answers called adapt answers. So, in the adapt answers, the variation functionality is generally in an adaptive manner. So in the adaptive answer, we have to first we have to define an operator pool, which is the collection of the operator definitions, and select one operator or several operators from pool and prepare the entire case with the current answer using the operator selected from the pool, and then perform the calculation of analytical gradient. Maybe this can be numerical gradient, but anyway, calculate the gradient for each operator in the pool. So it means that if the gradient is large, so it means the operator in the pool, the particular operator is very important to improve the wave function. So if the norm of the gradient vector is smaller than the threshold, all the gradient vectors are small, in that case, it's 6. Otherwise, go to step 6 and identify the operator having the largest gradient and add the operator to the rest of the answer. And then perform VQE to re-optimize all parameters. So in this case, the first task, the VQE starts with the operator with only several operators, and then iteratively performing the VQE by including another operator having the largest gradient in the pool. Another famous answer is Hugger-Eschen one. The basic idea of Hugger-Eschen answer is something like this. The wave function is entangled state. So if we can generate arbitrary entangled state, it can be regarded as an approximate wave function. So the functionality for the Hugger-Eschen answer is the structure is something like this. We have n qubit for the wave function phase, and usually we apply one qubit rotation J, and then perform another J, which can be 2 or 3, usually 2 qubit J, to generate the entanglement between the qubits, and then perform another rotation J, single qubit rotation J. And the functionality is repeated. This part is repeated D times. And the D is usually called as a layer, number of layers. So if we perform the this functionality with applying this gauge sequence 2 times, this corresponds to 2-layer Hugger-Eschen answers. So usually the functionality is shallower than that based on the unitary calculation answer. But important thing is function J doesn't necessarily to have a correspondence to electron excitation or de-excitations. And because because of this feature, the energy lowest state of the given Hamiltonian is obtained this way. So it means if we want to compute the neutral state, but in case the anionic state is the energy lower than the neutral state, we obtain the anionic state instead of the neutral state by using this VQE with Hugger-Eschen answers. So basically this is just optimizing the lowest energy state. So because of this feature, the VQE with Hugger-Eschen answers sometimes suffers from the kink shown here. This was reported in the Nature paper in 2017, this was reported from the IBM group. It calculated the potential energy curve of lithium hydride molecule, but the simulated results have some kind of barrier around here, potential barrier. Of course, this dotted line corresponds to the flux I, so there's no barrier. So why this kink appears? This is because of the nature of the mean field approximate state, raw mean field state will change around here. As soon as let's think about the Hartley-Fock, reflecting Hartley-Fock potential curve, the RHF curve consumption was this kind of curve, because RHF cannot describe the bond dissociation very correctly. And also the spin triplet ROHF case. The spin triplet ROHF case is the potential curve is something like this. So basically, this appearance of the kink means that the potential the quantum state obtained electron state changes from the spin singlet state to the triplet state. So in order to avoid such kink, a constraint VQE was reported. In the constraint VQE, we use the shifted Hamiltonian H gas, which consists of the original Hamiltonian and the penalty term. In this case, if we want to avoid the spin state switching, so we use the spin x-square operator as a penalty function. Because the x-square operator gives an eigenvalue x times x plus 1 by setting the term as x-square operator minus x target times x target plus 1. By setting this, the electron state having different quantum state, different spin quantum number, the energy of the quantum electron state having different quantum number, spin quantum number than the target state will push up by this penalty terms. And also, in this case, if we calculate the ms equal x target using the ms equal x target wave function, the quantum state, electron state having the spin quantum number smaller than the target spin quantum number of the target state doesn't contribute. So we don't have to apply a square. Just a absolute value is enough. And also another important thing is penalty term should be included in the parameter optimization step only. So for the final energy evaluation, one should use the original Hamiltonian H. In the Hawking Eskin answers, sometimes the number of electrons will change. If for example, as I said, we want to calculate the neutral state, but the anionic state has the lower energy that we can obtain the anionic state in the Hawking Eskin answer. But let's think about the function mapping based on Jordan-Wegener. In the Jordan-Wegener transformation, the synergy will change the number of electrons. So, but if we use the AG defined as shown here as an entangling gate, the number of electrons is always preserved because this A operator, the action of A operator can be calculated as shown here. It doesn't, it becomes the identity operator for 0 state and 1 state. And if we apply this A operator to, for example, 0 state, if we generate the linear combination of 0 and 1 state. So the number of qubits in the 1 state is preserved. So by applying this functionality, the number of electrons is always preserved if the John-Vega transformation is applied as a wave function mapping. And also, important procedure in VQE is error mitigation. Because the NIC devices are very noisy, we always think about the effect of errors. Applying quantum error correction is quite difficult on the NIC devices because the limited number of qubits and also limited length of coherent time. But instead, we can mitigate errors by performing additional measurement and post-processing. My example is measurement error mitigation. The detail is described in the this web page, in QPE web page. And let's think about the measurement appear the situation with the measurement error. Measurement error is we can obtain the 1 state although the quantum state is inside to 0 state, for example. So let's think about the just this kind of functionality. And this X gate is introduced as a state preparation. And just generate the quantum state and measure the quantum state. And if we remove these two power X gate, it can correspond to the starting the 0 state and just measure the quantum state. And if I perform the this functionality using IBM manual machine, the initial state is, for example, in the 0 state, apply 801.82 measuring, I think, 92, 192 measurements, I think. The measurement outcome are something like this. We can obtain 0 states, almost obtain 0 state, but we also obtain 1 state and 1 state with small probability. And if we start from the 0 state, of course, the largest probability is the 0 state. But still, we have an opportunity to obtain the 0 state or 1 state or 1 state. So we can, by performing this kind of quantum circuit, we can define this M matrix. So we can think about it starting from the ideal state, but because of the error, we can obtain the noisy outcome. So M can be constructed from these measurement outcomes. An idea is perform M inverse, apply M inverse to noisy measurement outcome. could recover the ideal one. This is the basic concept of the measure error mitigations. Another error mitigation technique is symmetry verification. As I said, in the Jordan-Wegener cases, the big flip, if the big flip occurs, it will change the number of electrons. For example, let us think about the hydrogen molecule in exclusivity basis. The wave function can be written as the linear combination 1100 and 0011 in the Jordan-Wegener case. This is a neutral state. But if big flip occurs on the rightmost theory, it will generate the linear combination anionic state and cationic state. So, in order to check if the big flip occurs or not, we can perform, this is a conventional from the circuit for the hardware efficient answers. We introduce one ancillary theory and then perform single gate. So let us think about the 1100 stage. This single operation transforms the 0 state to 1 state, and another this single gate will generate the 1 state, transform the 1 state to 0 state. The measured outcome is 0. But if this kind of flip occurs, big flip occurs, the measured outcome becomes 1. So if the measurement of the ancillary theory is 1, we can understand we can recognize the big flip occurs. So the situation, let's think about the situation with no big flip errors. The measured outcome of the ancillary theory is n electrons mod 2, modulo 2, in the case of Jordan-Wegener. But the presence of the big flip error, the measured outcome becomes n electron plus 1 modulo 2. So we can distinguish if the big flip occurs or not by measuring this ancillary theory. Usually the VQE is for the ground state calculations, but we can calculate the aesthetic state by using VQE. There are several approaches reported for the aesthetic state calculation, but the simplest one is using the orthogonality. This approach is very simple. First, we calculate the ground state using conventional VQE. And then, in order to calculate the first aesthetic state, we optimize or minimize this E1 dash, which is the energy of the first aesthetic state plus the overlap between psi0 and psi1. So if the aesthetic wave function is orthogonal to the ground state, this term becomes 0. So by using this approach, we can calculate the nth aesthetic state by minimizing this using this equation. So in order to perform this on the circuit, we have to evaluate the sphere overlap between the wave function psi k, psi n. But this term can be evaluated by using, for example, track test. Another approach for the aesthetic calculations is based on the subspace expansion. And this approach is very similar to the MRCI on classical computer, where reference wave function or multi-reference wave function is computed by using VQE. So in this approach, first, we optimize sorry, this not Q but theta to minimize the energy of ground state by using VQE, just perform conventional VQE. And then compute the Hamiltonian matrix of the form as shown here. This precise theta was obtained from the conventional VQE. So this can be initial calculation, for example. And this OI dagger and OJ are excitation operators. So if we select the OI and OJ as a 1 and 2 excitation operator, so this corresponds to MRCISD. Also, we have to compute the overlap between these two states. So by computing this matrix element, we can construct this expression and solve the generalized eigenvalue problem on classical computer to obtain the ground state and aesthetic state. So originally, this approach was proposed to error mitigation, but this approach can be also applied to the aesthetic state calculation. So in this approach, we think error, effect of error or noises, a concatenation from the other electronic state. But in order to perform this approach, we have to evaluate the expression value of this OI dagger HOJ. And Hamiltonian have four function operator, I mean the two fraction and two antecedent operators. Let us think about the OI and OJ are one and two operators. So in that case, is that this OI dagger and OJ consists of the one creation and one antecedent operators. So in order to calculate the expression value of this operator, we need four body reduced frequency matrix. Also in VQE, we can calculate the transition probability or octagon matrix element between the ground state and aesthetic state. In this approach, first we have to calculate the psi 0 and psi 1, for example, ground state and aesthetic state with function individually. And then evaluate the expression value of A, where A is an operator we want to calculate the off-diagonal terms. For example, Rij, for something, to calculate the transition dipole moment. So if we perform the conventional VQE, we can of course calculate the diagonal term of the expression value of the A operator. The next, we evaluate the expression value of A operator using phi psi and phi minus, phi plus and phi minus, where phi plus is defined as a linear positive linear combination of psi 0 and psi 1. And phi minus is a negative linear combination of psi 0 and minus and psi 1. And if we calculate the expression values by using this psi plus and psi minus, the measurement outcome can be calculated as shown here. So this includes some diagonal terms and off-diagonal terms. And diagonal term has the same sign between these two equations, but the off-diagonal term has opposite sign. So we can calculate the off-diagonal term by using this equation. So VQE is very useful because the functionality for the wave function preparation is very shallow or executable on the NIC devices. But one famous problem, there's one famous problem is the Barren plateau problem. For wide classes of the random functionality, the extension value of the observable concentrate to the array over surface space. So the probability that the gradient along any reasonable direction is non-zero to some fixed precision. It expresses small as a function of the number of qubits. So it means if the number of qubits will increase, the gradient of the parameter is almost zero. Almost of the vast potential surfaces. So it means that obtaining the correct ground state becomes very difficult. Another important point of VQE is the measurement cost. Because energy expectation value is computed by statistical manner, so statistical errors are unavoidable. The number of measurements required to obtain some energy precision E, epsilon, is something like this. So this equation includes norm of the Hamiltonian terms and energy precision. So it means if we want to make the energy precision to be half, we must perform 4 times larger number of measurements. And also this is because this is a norm of the Hamiltonian terms. And the largest norm of the Hamiltonian term usually comes from the electron-nuclear attraction interaction. So this W max becomes very large for molecules with heavier atoms because of the strong nuclear electron attraction. In that case, we have to apply many measurements to obtain the energy with some precision, desired precision. Most of the theoretical study on VQE uses the scalar vector simulator. If we use the scalar vector simulator, the expectation value can be calculated directly from the quantum state. So this corresponds to the infinite number of measurements. But in the real quantum machines, of course, the infinite number of measurements is impossible. So we have to perform some measurement at some, for example, 10,000 times or less. So we have to always bear in mind the statistical error. So let us think about the computational cost of VQE. So because VQE consists of basically 3 steps with function preparation, expectation value calculation, and parameter optimizations. For wave function preparation, if we use the unitary calculus answer, for example, the number of parameters correspond to will affect the depth of the parameter functionality. The number of parameters is something like this. And also, in order to perform Fermi-Cubic transformation, we need another computational cost, which arises from if we apply a Jordan-Wegener case, we need additional order n cost. If we perform Bragg-Kitaev cases, the additional computational cost is order log n. But if we use the hardware efficient answers, the number of parameters is usually n order nl, where L denotes the number of layers, and n is the number of qubits. An energy expression evaluation, the computational cost is about order n to the third power. This comes from the number of operator groups. And parameter optimization it strongly depends on the molecular system and optimization algorithm being used and initial parameters. But empirically, order n or greater. Maybe empirically the computation cost for parameter optimization almost proportional to the number of parameters. Important thing is note that the computation cost on classical computer is order n to the sixth power. So unfortunately there are misconceptions on VQE. By using quantum chemical calculation can be performed exponential faster than classical counterpart. And quantum chemical calculation can be accelerated by using VQE. But unfortunately, I think this is just a misconception. Because in the VQE, we calculate the approximate wave function, for example, by using unitary answers. So the computation cost is polynomial. But at the same time, the computation of approximate wave function on classical computers is also polynomial computation cost. And of course, the VQE is capable of computing the full CI wave function if the number of parameters is exponentially large. So, but in this case, the computation cost scale exponentially. So here, from the beginning, why the quantum chemical calculation is very difficult on classical computer. The obtained variation-based wave function, namely full CI, is very difficult because the number of variation parameters increase exponentially against the system size. And VQE calculates the wave function by variation optimization of the parameters. So number possibly scale exponentially against the system size towards the exact wave function. So using VQE doesn't directly mean that the quantum acceleration. This is a very important point. So finally, let me summarize today's talk by comparing quantum phase estimation on VQE. The classification of the algorithm can be written as shown here. Quantum phase estimation is a kind of fault-tolerant quantum computer algorithm. So it's very difficult to execute on the NIC devices. But VQE can be done on the NIC devices. But the wave function, the obtained wave function is full CI or taxi CI if we apply active space approximation in quantum phase estimation. But in VQE, the obtained wave function should be some approximate wave function, such as unitary cluster or heuristic ones. And quantum phase estimation, the energy eigenvalue can be calculated, except for the Bayesian phase estimation. But in the variation quantum eigensolver, we calculate the excitation value of the energy, not the eigenvalue. But the quantum theory for the QPE is very deep, so this is the reason why it's impossible for the NIC device. But quantum theory for the VQE is usually very shallow, enough to execute on the NIC device. And the computational cost scaling against the energy precision epsilon can be calculate as the 1 over epsilon in quantum phase expression. It means that in order to make the energy error to be half in the QPE, we have to apply twice longer time evolution. But in VQE, the energy precision depends on the statistical error. So in order to make the energy precision to be half, we have to apply 4 times larger number of measurements. So the measurement cost, computation cost increase. Not linearly, but square in the square form. Another important point is exponential speed up or just a speed up against the classical counterpart was theoretically guaranteed in quantum phase expansion. But the computation constraint of VQE is not thoroughly illustrated. So the speed, if the VQE can accelerate the quantum mechanical computation, is just unknown. Okay, so this is the end of today's talk. Thank you very much for your kind attention.
Thank you very much, Professor Sugisaki, for the very nice talk on VQE. So are there any questions? Dibajyoti has a couple of questions. So I will read out the questions one after the other. His first question is, does full trotterization in VQE correspond to complete decoupling among the various excitation operators?
So could you tell me the question again?
Oh, yes, sorry. So his question is, does the full trotterization in VQE correspond to complete decoupling among various excitation operators?
Decoupling, yes, basically.
Okay. I can read a second question. He is asking if it's okay for you to repeat the differences between adapt VQE and the normal VQE algorithms.
Okay, the adaptive VQE, in the normal VQE, first we define the parametric function circuit and then perform the variation optimization using the same parametric function circuit. But in the adaptive answers, the variation function circuit is generated sequentially in the iteration by including another execution operator including another execution operator, which is expected to have a large contribution to the energy. So in the adaptive VQE, we can think about the situation of we have the hundreds of the execution operators. In the conventional VQE, we generate the function circuit, including all the execution operators, and optimize the 100 parameters. But in adaptive VQE, first for example, we select 10 execution operators, and then perform the VQE using just the 10 execution operators with 10 variables. Of course, the computation is easier than the VQE with hundreds of parameters. But because the answers include only 10 execution operators, the obtained wave function may be found from the exact wave function. So in order to improve the wave function, we include some additional operator. and then perform the VQE, another VQE, using 11 parameters. And then perform another, and then select another operator by calculating the gradient, and then perform the another VQE with 12 parameters, and so on. And if the energy difference, energy change becomes very small than the previous step, the adaptive VQE is zero. So basically this is the approach to include the excitation operator having larger contributions. So the final wave function have usually smaller number of excitation operator than the conventional VQE. This is the basic idea. But of course, the computational cost, we have to include some computational cost to calculate the gradient. And also, we have to perform the VQE iterative manner by incrementing the excitation operators. This is the difference between conventional VQE and adaptive ansatz.
Thank you. Are there any other questions? If not, then let's thank Professor Sugisaki for a wonderful lecture today.
Thank you very much.
Thank you. See you all in the next lecture.
Okay.
Thank you.